All right. All right, so in this chapter, we're going to look at a different class of functions called the exponential and log functions. So before, the variable was always the base, and we were doing something to it. Like we were squaring it, cubing it, taking the square root, adding or subtracting those guys, and eventually we looked at very quickly rational functions when we took polynomials and divided one by another. Now we're going to interchange the roles of the base and the exponent. This time the base is going to be a number and the exponent's going to be the variable. So for instance, an exponential function, this is the new class of functions we're going to consider, is one for which the base is fixed and the exponent varies. So for example, 4 to the x, or 2 pi, which is a number, to the x minus 1. Those are called exponential functions. Now we're going to start off basic with just 2 to the x, right, and make some observations about its graph, and then we'll generalize to other bases. So as with anything with functions that we don't know about, we're going to plot some points, see what happens, connect them, and then deduce what the graph ought to look like based on what's happening in the input or the outputs. So if you look at this, there's no number to which I cannot raise 2, right? There's no restriction on the domain. And so I'm taking values, I'm going to start at 0. That's always a good place to start if it has a point at 0. It's the y-intercept. And then I'm going to take x values that are larger and smaller than 0 by equal steps on either side. All right, and so what I get here at 0, notice 2 to the 0 is always 1. Any number aside from 0 when raised to the 0 power is defined to be 1. So we know it crosses at the y-axis. If I put 1, 2, or 3 in for the x, I'm raising 2 to the first, second, and third power. Those are increasing. And notice that for every unit step in the x that I take, one step from 0 to 1, one step from 1 to 2, one step from 2 to 3, the function's actually doubling. And so it's getting larger very quickly. At 4, it would be 16. At 5, it would be 32. So this function is going to continue to rise very quickly. And in fact, the speed at which it rises will increase the larger the x gets. So it's pretty safe to say that as x gets large, it's going to get large. It's going to plus infinity. For negative inputs, let's go the same amount on the opposite side. We have -1, -2, -3 as the inputs. Now I'm using the same powers of 2, but now I'm going to be dividing by them instead because they have they're negative exponents. So 2 to the -1 is really 1 over 2 to the first. 2 to the -2 is 1 over 2 squared, and so on and so forth. So I'm dividing 1 by these powers of 2 over here that we're increasing very quickly. But we know that if the top of a fraction is the same and you increase the bottom, the fractional value gets smaller. And so you can see what happens with these 3 points, right? 1/2, 1/4, 1/8, they're getting cut in half every time for just a unit step in the x. They're getting very, very small. And furthermore, they're never negative, right? Because these are you're always dividing 1 by a positive number, and the top is never 0, right? The only way a fraction can equal 0 is if the numerator is 0. And so what we can deduce is that the larger the x gets in the negative direction, the smaller these y values get, but they're trapped by the x-axis, right? They're getting smaller. In fact, they're getting close to 0, but they never can hit 0 because they never become 0 in these values. And so what it suggests is that we have a horizontal asymptote being the x-axis as x goes to -infinity here. All right, so if you look at other graphs, so let's look at 3/2 to the x versus 3/10 to the x. If you look at 3/2 to the x, the graph looks basically the same as it did for 2 to the x, right? It crosses at 0, 1. In fact, so does this guy. And since this number is larger than 1, raising it to a power that's bigger than 1 will make it larger. So it looks just like 2 to the x, perhaps growing a little bit less fast, a little slower. This guy, however, 3/10 to the x, that base is between 0 and 1. And if you were to plot the values with a table here, in fact, I suggest you do so just to convince yourself, If you take values that are larger than 1, you're raising a number between 0 and 1 to a larger and larger power, the value is going to get smaller. But if you raise it to a negative number, all right, and then for negative powers of x, if you put in, you're going to flip over the 3/10, it becomes 10/3, which is larger than 1. So for negative inputs, it's going to get big. So to actually make a table just to convince yourself of that, you don't have to use 3/10, just use a number like a half or a third, just to kind of get a feel for what happens when you raise a number between 0 and 1 to that x. All right, but we're going to make these observations based on it. All right, so for b larger than 1, the graph of b to the x gets close to the x-axis as x gets more negative, and it grows rapidly up as x gets more positive. The exact opposite happens if the base is between 0 and 1. But in both cases, the line y equals 0 is a horizontal asymptote. All right. Furthermore, for any base that you use that's positive, the output b to the x is positive, and so the graph of any exponential function does not cross the x-axis. Right, so this equation, b to the x equals 0, has no solution. Okay, so now just some simple calculations just to remind you how to use the exponent rules, because we're going to have to solve equations involving these exponential functions. So first, let's just take a look at these. If you want to simplify a product of this form, notice that they have the same base. And so what we know from our exponent rules, if you multiply powers of the same base, you add the powers. And so this becomes 2 to the sum of those guys, which is 2x plus 1. Okay. If you want to simplify this, remember that if you take a power to a power, you multiply the powers. So that's what we're doing here. And then we eventually want to rewrite this as a single quantity, not a product of quantities, but a single quantity. So to that end, I'm going to distribute the 2 through here to get 4 to the 2x minus 2. And I'm going to rewrite the 16 as 4 squared. Okay. Then what we have is a product of powers of the same base. I know I can add the powers. And so what I'm going to get is 4 to the 2x. All right, so that is one way to represent this more simply. Another way is that you can rewrite this. Remember, you can view 2 to the x, or 2x as 2 times x. And so if I wrote 4 squared to the x, to simplify this, I would have just multiplied the 2 and the x together, right, to get this. Nice thing is 4 squared is 16, and so I can further simplify this guy as 16 to the x. All right, so you try this one. We can just talk through it, I guess, too. You have a quotient to a power. The quotient of terms of the same base, you subtract the powers. So I'm doing inside. And then I combine the like terms after subtracting the 2x and the 6. And then if you raise a power to a power, you multiply the powers. And so I multiply half times that guy to get x plus 3. Okay. If you have kind of a rusty about the exponent rules, go back to chapter 0, and you can take a look at those. All right, so now we're going to solve some exponential equations. And the general idea here, one of the properties that is helpful is that if you have 2 real numbers that are equal, right, and a is positive, then a is positive and not equal to 1. That's important. Okay, so fix that in your PDF there. Okay, then you can raise both sides. You can take the a of both sides if you want. So in other words, if you have 2 inputs that are the same, then using them as exponents of the same base results in the same quantity. All right, so what do I mean by that? Well, let's take a look at this guy. Let's suppose we want to solve 2 to the x minus 5 equals 8. What we're going to do is I'm going to express 8 as 2 to the 3rd. All right, so then what we have is an equation in which each side is an exponential, and it just so happens that base that I'm using is the same on both sides. But by this property, if you have an equation of this form where you have the same base being raised to different quantities on both sides, the only way that can happen is if the exponents themselves are the same. And so that's what I'm going to do here. I know if this is true, the only way that can happen is if x minus 5 is equal to 3. Those are the exponents. But I can solve that. Just add 5 to both sides to get x equals 8. All right, and so a technique that is often useful when solving exponential equations is to at least try to rewrite both sides as powers of the same base, and then you can get rid of the exponential part by equating the exponents. Doesn't always work, right? Because there's nothing saying you have to be able to rewrite each side as powers of the single base, but when it does, it's very useful. All right, this one is the same, but slightly more complicated. You want to express each side as powers of the same base. You have to choose the base though, right? And so notice the left-hand side is already 3 to something. So why don't we try to write the right-hand side as 3 to something, right? To that end, notice that 9 is 3 squared. So if I multiply 3 squared times 3 to the x minus 1, I have a product of powers of the same base on the right. I'm going to add those powers. And so I get 3 to the x plus 1. But now I've rewritten this equation as one of this form where I have the same base being used on both sides. And so I know the only way that can happen is if the exponents themselves are equal, right? And then to solve this, you subtract x from both sides and you get x equals 1. Okay. All right. This just gives you another approach to it. So there's nothing saying I had to keep it in that form. I could have divided both sides by 3 to the x minus 1 first and gone through the same process. Either way you approach this, if you're using the same underlying strategy and you don't use the exponent rules incorrectly, you'll get the same answer. All right, go ahead and try this your turn, and we'll talk, we'll talk about that once you actually try it. Okay, so what I decided to do here, you can approach it one of two ways. What I decided to do is multiply both sides by 4 to the x. That gives a 1 on the right and a product of powers of 4 on the left, which I can reduce by, or simplify rather, by adding the exponents. And so what I get on the left is 4 to the 3x minus 3, and I'm going to represent 1 as 4 to the 0, right? Because again, I want to use that property that tells me if I can rewrite both sides as powers of the same base, I equate the exponents. But I can't do that until I rewrote the right side as 4 to something. All right, so now once we've done that, we know that 3x minus 3 has to be 0, and to solve that for x, you get x equal to 1. Right, so that's one approach to this. The other approach, the other natural approach would be to rewrite the right-hand side as 4 to the negative x, and then immediately conclude that the exponents 2x minus 3 and negative x have to be equal. So in some sense, that's even a more direct approach than what I used. In this example, example 5, notice that you can't use 25 or 125 as the base, right? So I'm going to rewrite each of these as a power of 5. 125 is 5 cubed, 25 is 5 squared. And so I'm going to rewrite the 125 to the x as 5 cubed to the x. And I'm going to rewrite 5 or 25 as 5 squared. But I still have to write this left side as 5 to something, right? And so I get 5 to the 3x on the left and 5 squared on the right. And so I'm going to equate 3x and 2, right? Since I now have both sides as powers of 5, I equate the exponents, and then I solve that for x to get x equals 2/3. All right. Another number that comes up is the number e, right? And so, so the number e is approximately 2.71828 ... It's actually irrational, and it turns out to be a result of looking at what happens to this quantity as n gets very, very large, right? So if you were to actually go ahead and fill this in, right, for these values of n, find those values, you'll find that you actually get these closer and closer to that number 2.71828. What? All right. Now, if you go through here, if e is just a number, you're just going to apply the same exponent rules that you would normally, right? So to simplify this, I'm going to rewrite this as e to the, well, okay, so first simplify this to write this is a power to a power. And so I'm going to multiply the powers to get e to the 2 times 1 minus x. And then to combine these, it's a product of powers with the same base. I'm going to add the powers, right? Well, this power is just 2 minus 2x, right? So if I add it to the 3x and simplify, I get e to the x plus 2. Right? So you treat these just like you did when it was 2 or 4 in here. E is just another number, just you can't write it out with a terminating decimal since it's irrational. All right, for this guy, let's actually just walk through this one together. You have an equation of the form e to the x to something equals e to the 10th. What I'm going to, again, attempt to do is rewrite each side as powers of the same base. And so here, I'm going to rewrite this guy using a power to a power rule. I'm going to multiply those powers. Right? And so this equation implies that since I have both sides as e to something, I'm going to equate those exponents to get that equation, and then subtract 10 from both sides to get this guy. But that factors as x minus 5 times x plus 2. And so if you set each factor equal to 0, you get 5 and negative 2. All right, let's look at this example. So this will look familiar in the sense that we did this for positive integer powers. We did it for radical x, cube root of x, and negative integer powers of x before, right? And also for 1 over x and 1 over x squared, right? So it's the same questions we've been asking all along, but now for a different class of functions. And so here we're going to start off with just 2 to the x, and we want to graph it using the translation and reflection results. So the first thing we'll do here, if you subtract 4 from the input, you're moving 2 to the x to the right 4 units. And if you add 3 to that, you're moving it up 3. Keep in mind that with the exponential functions, since the domain is all reals, moving a function left or right doesn't affect the domain. It remains all reals. What is affected is the range if you move it up or down, right? And not only is that range going to be affected, but the location of the horizontal asymptote itself is affected. And so here, if I look at our graph, if I moved it up 3 units, notice that that asymptote moved up from being the x-axis to now being the line y equals 3, right? But the general shape is the same. Okay? The domain is all reals. The range, well, the old range would have been from positive 0 to infinity, or positive 0 to positive infinity, not including 0. So now, since I moved everything up 3 units, the range is going to be from 3 to infinity, not including 3. So it's an open interval. The asymptotes we've already mentioned. There are no vertical asymptotes, but the horizontal one is y equals 3. The y-intercept is obtained by plugging in 0 for x. And so if I plug in 0, I get 2 to the minus 4 plus 3, which is just 3 plus a 16th, or 3 and a 16th. And in terms of x-intercepts, well, we can reason 2 ways. We can literally set this equal to 0 and solve, or try to solve for x. If you do that, the first step would be to take the 3 to the right side. And so you'd have the equation 2 to the x minus 4 equals minus 3. But remember, 2 to the x minus 4 is always positive. And so it can never equal a negative number. So that equation would have no solution. And so there would be no x-intercepts. So you can argue that way. Or you could argue from our graph that since we moved 2 to the x up 3 units, and it never goes below its asymptote of y equals 3, it never can actually cross the x-axis, right? So that's probably a more pragmatic way of doing that. Notice that it actually is increasing, right? So from left to right, it's always going up, even slowly initially, but it's still always going up. And so the function's 1-to-1, and hence it has an inverse. The problem is we don't yet know how to compute an inverse of an exponential. We'll have to wait until we talk about logs to be able to do that. All right, you go ahead and try this one and then check yourself once you're finished. All right, so for this guy, we're going to move it to the left 2 units first, then reflect over the x-axis, and then move it up 1 unit. All right, and so 2 units left, reflect over the x, and then shift it up, we get this graph. Okay. The domain of all exponentials is all reals. The range is affected because we've shifted it vertically and we flipped it. Right, so first, if we flipped it over the x-axis, the range would have been, if we stopped there, the range would have been minus infinity to 0, not including 0. But then I moved it up 1 unit. So now the range will be minus infinity to minus 1, not including minus 1. Or positive 1, rather, pardon. All right. The line y equals 1 is the new asymptote because we moved it up from the x-axis up 1 unit. The y-intercept is obtained by plugging in 0 for x. And so if I plug in 0 for x here, you get 1 minus e squared. Right? And then if you want to find the x-intercepts, we would have to set this equal to 0 and solve for x. Problem is we can't yet find those because you'd have to literally know how to undo an exponential. That is, we need to know what the inverse would be. So the equation's all we can give you at this time, and that equation is this guy. Okay? And the last one was does it have an inverse? Well, the function's 1-to-1, and so it does have an inverse because it's always decreasing on its domain. So yeah, it has an inverse, but we'll have to wait to find that until the next couple sections. All right, so go ahead and give these homeworks a try. They're all basically the same, on the same topic, not even that bad this time, because I want you to concentrate on the exponential themselves and see what you get. All right, take it easy.